2, instant response, and this is the last lecture. There we are. So this is the last lecture. We're going to finish investigating Windows system. There's one more class, but I'm not going to do any lecture. I'll just help students that have questions about projects. And then there's the final exam available this week. So, and you should be able to see your total in Canvas and the point total in any announcements, showing you what total you need to get different grades. So you should be able to figure out how much more you need to do to get the grade you want. All right, so let's take a look at the last investigating Windows system stuff, which is here. All right, so we're going to talk about interactive sessions, memory forensics, and persistence mechanisms, just more artifacts you look for on Windows systems. So interactive sessions are when you have control of the machine, like a keyboard and a mouse, you send commands and it responds. So you can log in directly at the console, the way you normally use a laptop, or you can connect with Microsoft's remote desktop protocol, the way we're connecting to Azure mostly, or you can use other software like VNC or something that does essentially the same thing, lets you remote control a machine. All those are interactive sessions. Now, link files, every opened file, Microsoft creates a link file to the opened file, so it'll populate this recent files list. So this is actually quite useful. It's a separate list for each user profile, and therefore you see every file that that person has opened. So they're here, they're in your app data roaming subfolder of your username. Down here there's a recent folder showing various types of things that have been opened recently. And so you'll find the full file path. If it's on a network share, you'll find that. You find attributes and size, and a bunch of creating dates, and a unique identifier. So it's really quite useful. And you can make a timeline. You can line them up, and then you'll just see what a user did. They went here, they went here, they went here, they went here. So very handy. Then there are jump lists. Down at the taskbar, ever since Windows 7, and it's also present in Windows 10 and 11, there are these icons at the bottom, and when you right-click them, you'll see the recently opened things here. Pinned things and recently opened things. So there's a separate recently opened list for each one of these icons. So if you have a Word icon, it'll show you recently opened Word files. This File Explorer is showing me the recently opened things that have been used with that icon, and so on. Those things are called jump lists, and they're stored here, also in app data roaming, various destinations. And it's not human readable, it's stored in some binary format, so you need to download a tool to analyze it, although I think, I imagine it's probably in Velociraptor, although I didn't find it here when I looked. Maybe, I'm not sure if that one's in Velociraptor. I bet it is, but last semester I added all the Velociraptor links I could find. Maybe not. Anyway, so the recycle bin, too, of course, contains files deleted from the hard disk. Not everything goes in the recycle bin. Things that are too large can't go in, things are deleted from a command prompt don't go in, and so on. But most things that you delete in the Windows graphical environment go in the recycle bin for a while. Eventually, the older ones are deleted to keep it less than 15% of your drive space. You can adjust that number. But anyway, you can examine the recycle bin. There's a command line tool called RIFIUD2, which will give you a list of everything in the recycle bin, and there's a Velociraptor tool too to give you everything in the recycle bin, which is good to know. And of course, this is very useful because very often criminals doing bad things will try to hide their stuff by putting it in the recycle bin, thinking they're getting rid of the evidence. All right, and then there's memory forensics. So in RAM, you have what's currently happening on the machine. Every running process has some memory regions it's using, network connections, drivers. Often there are user credentials in RAM. I don't know, put it in this class, but a lot of these classes we've been stealing password manager credentials from browser processes running in RAM. You'll find portions of other things like registry and event log, previously executed console commands, some clear text data like notepad files and such, and other data structures. So a lot of things are in the RAM. And the RAM is just a block of memory. You need a tool to parse it. And anyway, there's also other things. The main RAM you talk about is the physical RAM chips. That's the main memory, which is used to do almost everything, and it forgets when you turn the power off. Then there are things on the disk. And the page file is data that was moved out of RAM and put on the hard disk. Now, the original explanation of the page file is when you have so many things open that you run out of RAM, then things move from the page file to the disk to make room. But Windows does not work that way. Windows just randomly takes stuff out of RAM and puts it in the page file, even when you're not using much RAM. It is very strange, so you will find lots of strange things in the page file, and it's just sitting there, pagefile.sys. In Linux, it only uses the page file when it needs to, and you can make a system with no page file, and it's fine. Windows expects there to be a page file, and it uses it all the time, even when you're not using much RAM. Now, then there's crash dumps. When the machine dies with a blue screen of death, which means it has a fault in a kernel routine that it cannot recover from, then it can dump the memory. By default, it only dumps the kernel memory because that's where the fault probably is, but you can configure it to make a smaller complete memory dump. If these are turned on, which is not common, then a crash will create a complete memory dump, which is a perfectly fine forensic image. Everything in memory is there, every process, so that would be nice. And you'll find it in the local app data crash dumps, but you would have to turn on that memory dump feature first. Now that I think about it, that might be the coolest way to get a memory image from a Windows machine. I'm using forensic tools, but I don't know why we don't just use a crash dump for it. Anyway, right, so hibernation files are another way. When your machine hibernates, it puts the full contents of RAM on disk in Hiberfile. In earlier versions, this was just a one-to-one copy of the RAM. Now it's compressed, but Volatility can parse it. And Volatility is the most powerful memory analysis tool, the main one everybody uses. It can find everything, find every process name, every process command line, every network connection, and many, many other things. It does have to have a structure for your exact version of Windows. So you have to download a configuration file to tell it how each version of Windows uses memory. And so here's an example for Windows 2008 Service Pack 1. This is an old file I was working on, a memory dump. And you can run Python vol.py, that's volatility. Then you give it a command of what you want to extract, and this is getting the process list. So here's a list of every running process with the process ID, the parent process ID, and the time it started, and so on. So yeah, I see a lot of these service hosts. It's the same stuff you'd see in Process Explorer, but you're seeing it from a memory image. You see what was running when that memory image was taken. Here's a DNS process, here's an FTP server running, and so on. Everything's there. All right, let's take a look at a Kahoot, which is 12C1, this one. Well, that's good. It's nice to have more than 3. Although one of them looks pretty alarmed here. Definitely pretty alarmed. I'll wait for the end of the song. All right. All right, so you right-click a taskbar item, and what do you see? That's the jump list, all right. Oh, looks like we have 5 people, but only 4 show up there. Anyway, all right, maybe we'll have 5. All right, so which item can you only get from a live acquisition? So that's RAM. You have to do a live acquisition to get. There is no way to get a static acquisition of RAM. When you turn the power off, the RAM forgets. So you have to do a live acquisition, which is considered a less perfect forensic technique. It means you have to change the system while measuring it. So when you take a RAM image, some of what's in that RAM image is the tool you use to collect the RAM, and you just have to be aware of that. All right? So which one contains the entire contents of RAM? That's the hibernation file. The crash dump typically does not. Like I say, only in rare cases would it have everything, but the hibernation file always does. All right, and which one has only kernel memory by default? Yeah, that's the crash dump. All right. Nurses doesn't care about the points. Have to tell me their real name if they want to get their points. All right, so let's go here. All right, and so handles are objects that you use to refer to things. Like if you open a file, you get a file handle. You open a device, you get a file device. It's just an object in memory, and this can help with analyzing malware. Mutexes or mutants are labels in memory that can be seen by other processes, so they provide some degree of inter-process communication. So you can, for example, put up a mutant showing that this resource is in use and no other process should use it until I'm done using it, that sort of thing. And you use by malware to mark the infected box so the malware doesn't reinfect it. Here's the Zeus malware. When you're infected by Zeus, this is looking at an image, a memory image of a Zeus-infected machine, and you see this mutant called Avira 2108. That is the tag that Zeus puts on machines when it's infected. And if Zeus was run again, it notices that and doesn't reinfect it. And since they have a nice hard-coded thing that never changes like that, that's a useful indicator of compromise to use to detect machines infected with Zeus. And here's what you see if you go to Notepad and you view the handles. You'll see handles to files that are open and some registry keys that are open. And down here there's a mutant. And then there's some Windows station things, whatever those are. Windows, station, anyway. So they're handles to various objects. There's a bunch of handles used by every process. They don't all have mutants, but they all have handles of one kind or another. And Velociraptor can detect the mutants. Like you can do everything else, that's why Velociraptor is your all-purpose tool that saves you having to find a whole bunch of separate tools to get all these different artifacts. So each process has a virtual address space, including several memory regions. So it has certain memory regions allocated to that process, and therefore some disk space in the page file. The OS swaps data in and out. So there is a virtual address descriptor tree, which specifies the memory regions used by each process. You can view it with this tool, vmap, which is a process internals tool. It will show you the map. So it's quite complicated. Here it is just for Notepad. Just for the process Notepad, you have all these memory sections. It looks more complicated than what you see if you look in a debugger, like we've done before. But anyway, you can view the detailed memory map with this mmap tool. And Velociraptor can do it too. It can examine the VAD, which is the record that keeps track of what memory is assigned to each process. So it'll give you the memory regions of each running process, or of course you can configure a parameter and get it for just one process. That's why Velociraptor is so great. Pretty much everything can be done easily through Velociraptor. All right, then you might have DILs. I said the number one way you compromise a machine is with DIL injection. So it is very common that an attacker has put a malicious DIL on your machine and you'd like to find it. So one simple thing to do is look for valid digital signatures. And this is why when I was talking about the news earlier, the fact that one of the Android trusted certificates has leaked and is being used to sign malware is very bad. When you see something signed by a legitimate company like Google or Microsoft, the idea is you can trust it. You don't need to worry about it. But if they're going to be losing the certificates, then that fouls up that trust. So anyway, normally, if you see a good digital signature from a reputable company, you don't worry about that file anymore. You can also have a list of known good and known bad hash values and look for those. And you can look for other evidence that something's wrong with this DIL, like if malware is loading a DIL surreptitiously, or I'm not quite sure it means running code in memory. Anyway, so here's the DILs you see in Notepad. We've seen this sort of thing before. Just a whole lot of system DILs. Advanced API, kernel32.dil, msvcrt.dil, just the sort of things you normally see. Even the simplest application usually has a whole bunch of libraries it's using. And they're bad. Oh, I see. Someone has told me who they are. Good. Let me make a note of that name for Gnosis. All right. Make a note of it before anything slips by. Good. All right. And so Velociraptor can load the system DILs. This will enumerate the DILs loaded by system process, and it will include the hash value and the certificate information, which is very handy because you can look at the certificate and detect if it's a known, signed by some company you trust, and you can take the hash value and send it someplace like VirusTotal to see if it's known malicious, and so that's very handy. Then you might want to know network connections, loaded drivers, console commands, strings, and credentials from memory. All these things are typically available in memory.
Is a certificate inside the DIL?
The signature is in the DIL. And I think you can see the certificate that was used to sign it. So yeah, the digital certificate is the public part. I mean, to create the certificate and the signature, you have to use the private key, which is, of course, not there. That's only on the server that signed it.
But in the DIL, you can see the signature, right? And
yes.
Who has?
Absolutely. That's the whole point. So you can see when you get the DIL, it has a signature, and you can view it, and you can see if the signature matches. And if it does, and if the company name is like a reputable company name, then you have a high degree of confidence that it's not malicious. Although, of course, sometimes it happens, like the SolarWinds attack. The Russians compromised the development environment of SolarWinds, and they pushed out updates from the SolarWinds servers that included malware and were signed by SolarWinds. So I mean, if somebody compromises your development team at a company, then they can put malware in your stuff that's signed, and that's really bad, because this is something I often hear Paul on Paul Security Weekly talk about. If you can't trust these digital signatures, then what are you supposed to do? How are you supposed to know? Most of us just trust them, because otherwise you will go mad. But it doesn't. There's nothing perfect. But normally, if it's signed by somebody, then by a reputable company, then you don't have to worry about it. Anyway, so the Pagefile has no structure intrinsically, just like the memory, but you can search for strings. One thing to be aware of is that antivirus and intrusion detection systems will leave signatures in the Pagefile. There was a forensic case I heard about from one of my teachers where they thought someone had infected a machine with all sorts of malware. They thought they'd been viewing all these porn sites because they looked into memory and found them, but it was their anti-malware product that was looking for those sites to block them. So the fact, you'll see, of course, a bunch of suspicious strings in there because those are the strings the anti-malware is looking for. It doesn't mean you're infected with all those things, but it will have strings that match some of those things. So it's a thing to be aware of. Windows can be set to clear the Pagefile on shutdown, but it doesn't do that by default. All right.
You look at how to clear it?
Yeah, it's in advanced settings, I think. You go to computer properties and advanced settings. There's an option you can turn on. It's not popular because it makes shutdown slower. But it's something you might do if you want to increase your privacy, like some people delete their cookies all the time in the same kind of spirit. Of course, it's not a forensic wipe of that. So even if you delete it, it's probably still remaining on the disk as a deleted file. If you really want to maintain your privacy, then the thing to do is install a tool like steganography. A tool steganography, you can configure it to forensically wipe everything that's deleted. And that's, of course, taking a lot more time, but it means your machine will not have any remnant files on it. Or you can just get a modern machine with an SSD, and then almost all of that happens automatically. Deleting something means it's totally erased.
SSD, it does it by the
garbage collection. It runs garbage collection in the background. So if you delete a file,
collection run by the software or
it's run by the firmware on the hard drive. on the SSD. And you must have trim enabled so that when you delete a file, the SSD knows that file has been deleted. It then performs a garbage collection process to clear up the unused sectors. And so if you don't have an up-to-date driver, see, old hard drives, when you delete a file on a hard drive, a rotating hard drive does not know a file has been deleted, because all it does is write to the block, and it writes to like a block on the MBR saying this file is, but it doesn't understand what it means. So it changes a bit in the MBR saying these sectors are no longer in use, but it doesn't know that that file has been deleted. It doesn't understand what file system is being used or anything. It's just a dumb device. Write a block here, write a block here. But SSDs are smarter if you have trim. They actually understand what the files are, and they understand when a file has been deleted for this reason, because SSDs, it's very slow to delete files. So if you had to delete space when saving a file, it would slow it down. So in the background, when you're not using it, it is hunting the files and deleting them so to be ready to store more data later. And that's the garbage collection, and it's powered by trim. So it's cool. It doesn't always work, but it frequently means that SSDs don't have any significant amount of undeleted data available to recover. Anyway, so here's some in-memory attacks, process injection, and hooking, and we were talking about these in the malware analysis class, and here they are because it's a similar issue. So you can inject code into a process. This is an in-memory attack. You do not change a disk file. You're running some process like a browser, and what you do is you suspend that process to stop it, you modify the code in memory, and then resume its execution. And now it will continue to run with modified code. So that's the injected process. There's no record kept anywhere that this has happened. It's not like loading a DIL. It's just a write operation there. So it's pretty sneaky. And you can do it with, now you can do it with Windows APIs. You force the target process to load a malicious DIL, or that's the most common way, or the more difficult way, you directly write malicious code to the process's memory, and then you have to carefully write code that will not make it crash. And all right, and that's process replacement. You launch an executable, then you suspend it, then you overwrite the memory malicious code and unsuspend it to execute. The easiest thing is to just destroy the original code. So you take something like a service host that's running in the background, that's running some service that you probably don't care about, and you just trash it. Just destroy it and put in different code. That's the easiest thing to do. What's more difficult is to carefully modify it so it continues to have its original purpose plus the malicious purpose. Those are the more complicated Trojans to set up. All right, so here's other things you might do to detect that. No memory section should ever have read, write, and execute all turned on. That is not recommended. It's not forbidden, but it is not recommended. It's a very old technique that led to the early buffer overflows. All modern operating systems don't do that. And if someone does that, that's a strong indication that somebody's doing something malicious. Also, if you have a process and the sections in RAM do not match the sections on the disk, that indicates that somebody's been modifying the memory. Because when you load a process from disk, executable, it should just take the sections and write them to disk, to memory, just the way they are. Now the spacing between them will change because they're packed closely together on the disk and they're spread out in RAM, but each section should still have the same hash and every byte the same. And if it doesn't, then somebody's been modifying the RAM image. So Sysmon can detect this. Remember, Sysmon is the Windows tool that detects suspicious activities, and here it is detecting inject process.exe. That's the name of it. But down here it had found information Sysmon create remote thread detected. So it detected the API call to create a remote thread, which is how you do this. You connect to some other thread in a different process, and then you can start changing it. So this is a system call that is suspicious. All right, and then there's persistent mechanisms. These are things that mean if someone reboots the machine, it will restart your malware, putting you back in control of it instead of stopping the malware. Well, it'll stop briefly, but when they turn the machine back on, you'll be back in. So you just need something that automatically launches it. There's keys in the registry that do it, and you can have DIL load order hijacking, so when it starts something, it loads the same DIL back in, and so on. There's various ways to do it. Hooking is another way to do this. You can add a hook so that when you make an API call that uses something like a file, there's a hook that says, before you do that, go run this other code. And this is what antivirus does. You double click a file to open it, and it hooks that. Wait, before you open that file, run down here and scan it. It's a legitimate part of Windows. A lot of tools insert hooks, but malware can insert hooks too. And so rootkits can use hooking to hide files. So every time you run Windows Explorer to open a disk, before it draws a picture of an icon of a file, it hooks and says, wait, if it's a file I don't want you to see, don't let them see it. It can do things like that, network connections and so on. Keyloggers can set hooks on the keyboard events, like key presses. Or they can keep running called getAsync key streak to constantly strobe to see if a key is up or down, which is a less efficient way to do it. But there are two different ways to record when key presses are used. So you can manipulate a process's import address table right in the PE header. So now when it tries to call a Windows API function, it will call some other function, change one of the addresses. So now it'll that one process will have a different consequence. You can hook internal structures like the interrupt description table or the SSDT is the way rootkits worked for a long time up through about Vista and Windows 2008. That would hook the kernel structures, so every process that tries to call Windows API calls would be calling modified Windows API calls. This is very much prevented on modern Windows systems by kernel patch protection. So I don't know how modern rootkits work in the kernel. This is the original kind of kernel rootkit that I used to have in my malware analysis course, and I haven't learned how the later modern rootkits work because Microsoft finally stopped this with kernel patch protection. And so here's the output of a volatility plugin on a system infected with Zeus. This will look for API hooks, and it shows an inline hook to the HTTP send request. So here it's detected a user mode hook. This is a trampoline. And you can see here is the HTTP requests, win-inet-dil. This is a Microsoft API call in the win-inet-dil library that's supposed to do an HTTP request. And when you enter the code here, the very first line is a jump somewhere else. That's what malware usually does. Normally, it would be setting up the preamble, pushing things on the stack, arranging a new stack frame, which is what's happening down here. But when you hook it, you change the first line to jump somewhere, do some stuff up here, and then come back. And that's what you typically do. You'll jump down here. You'll say, well, do I want to let you make this network connection? If I do, go back here and just continue normal stuff. If I want to lie to you, then block it. Tell you can't make that connection or something. This is how you typically do it. And that's a malicious hook. All right, that's what Zeus did. So to get your memory image, or what you can acquire the image with FTK Imager or dump it or memorize or Velociraptor, and many tools can make memory images. And once you've got a memory image, you can analyze it. The main tools are memorize and volatility that do it. So let's take a look at another Kahoot, which is going to be 12C2. Good. Unsure, all right. The last time somebody wandered in during the Kahoots and left before they were over, so that was a little strange. It can happen though. I turned it on so people can join during the game. All right, let's carry on. All right, so a kernel data structure that shows how memory is used by a process. That's the VAD. And let me go get the right name. I forget what it stands for. Virtual address descriptor. That's what tells it these memory sections that are used by a process. All right. All right, which one will have malware signatures even when there's no malware on the system? The Pagefile has sections of memory, and if it gets the section of memory that includes your antivirus, it will include malware signatures. All right, what technique is most likely to be malicious? Yep, process injection is the only attack. The rest of those are all normal things. All right. And which one is malware using to prevent reinfection? Yep, a mutant is a way to tag a box so you can tell it's infected. All right. Good. Let's go back to here then. All right. So, persistence mechanisms. There's other ways to do it, like the startup folders, scheduled tasks, modifying system binaries, the sticky keys attack, and DIL load order hijacking. So startup folders, this is the simplest and most direct thing. That's what they've been for. There's a folder ending in startup, and if you put a shortcut to something there, it will automatically load it every time you log in. It used to be on Windows XP, you could just right-click the Start button and explore, and it would put you in the startup folder. Now it's harder to get there. It's in this long path. But anyway, there is a startup folder, and this is the logical place to start something. If you're not trying to be sneaky, if it's a legitimate program, you just put a shortcut in the startup folder. That's you'll find normal things there. You can use scheduled tasks. You can use the @ command at the command prompt, or scheduled tasks, or you can use the graphical task scheduler. This is the equivalent of the Linux cron tab. You can just tell it to do a process at every startup, every hour, every day, or according to any schedule you want, automatically start tasks. And when you do that, every time you boot the machine, it consults the scheduled tasks utility, and it creates a bunch of job files in system root task. And these job files are what's used to launch the task. They tell it what to launch and when to launch it. And every time you reboot, it recreates these job files, setting up like you would your schedule. Here, I have to do this, I have to do that, I have to do that, like loading its calendar. You can modify an existing binary. There's a whole bunch of things that are automatically loaded, running in the background all the time. Typically DIL's loaded by service host, and you could just modify one of them to have extra properties, and Microsoft and Windows would automatically load it. So typically what you do is you modify it to have malicious code, then you timestamp it to change all the timestamps back to some normal time so it won't be obvious it's been modified. Now if you do that, it will change the MD5 hash and break the signature. So if it's signed code, it will no longer have a valid signature, but not all legitimate binaries are signed, and as we've seen, Microsoft does not always enforce the signature either. So it might run anyway. If you choose a careful one, you can choose one that's not signed, and then it won't matter if you break the signature. All right, so I mentioned before, the easiest way to put malware in a file is to just destroy the current functionality of the file and just replace the code with malicious code. That's one attack, but that's a very sloppy attack, and it might cause your Windows to crash or that process to crash. So it's you're more likely to, the best thing to do is to go for a non-critical executable library. Windows is running hundreds of things. Many of them are ridiculous things you don't probably use, and so you can mess them up, and if they crash, the user will not notice. That's one logical place to go. So Windows File Protection was the old version of Windows, but that was easily bypassed, so they changed it to Windows Resource Protection, and this is considered much stronger. So the processes that are protected by this, it's hard to modify those files. Now, the sticky keys attack is another one that dates from Windows XP and earlier mostly. If you press the Shift key 5 times before you log in, the on-screen keyboard will come on. So you can log in because you're telling it, I don't have the dexterity to use a normal keyboard, so I'm going to use some other input device. Now, what you can do is that launches something called sethc.exe, and you can replace that file with a different file, like cmd.exe, and then if you press the Shift key 5 times, it will launch a command shell. This is an old-fashioned way to get into a machine. It was quite popular up through Windows XP. So on Vista, Microsoft fixed it. They made it so you can't do that anymore. But there is another way to get the same result. You set cmd as a debugger for sethc here. And so if you do that, then again, it will still launch a command prompt. So that was the modified version of that worked. And Windows Defender can now accept that. As of 2018, Windows Defender will protect you from that also. So, that's the way it is. Every hack works only until Microsoft patches it, and then you have another hack and another hack. And by the way, patches are usually pretty sloppy. I was talking in the news earlier about that Spanish company selling exploit kits. They also said many of their exploits you could call them 0 days. They're things that were patched, but all you had to do was modify it a little bit and it would go through the patch, which is very common. So you can, usually if you do vuln reports and your company listens to you and fixes it, you usually go through 2 or 3 cycles of this. They say they fixed it, you test it, and you say, no, you didn't fix it. All I have to do is change it a little bit and it still gets in, and then they have to patch it again and again. That is usually how it goes, because the defenders usually don't want to make big changes, and they try to make a little change, but it's not that hard to modify the exploit to pass through it.
Is it legal to do malware as a service?
Is it legal to do malware as a service? Well,
the Spanish company is doing?
Well, yeah, that's a very good question. What the Spanish company is doing, it's selling malware to people who then use it. I mean, technically, I think it largely is legal. For example, you can sell a gun, and then people use the gun to commit a crime, but you didn't commit a crime, as long as you obeyed whatever the rules are. People argue about it. What happens is they get a bad reputation, like they drove them out of the business, because the Israeli company, NSO, did it for years, but they claimed that they would not sell it to oppressive regimes. And then it came out that they were selling it to nations that everybody hated, and so the good nations quit buying from them. So it was not, they didn't put them in jail, though. I think they just sort of boycotted them. Everybody said, we're not. Yeah, so I don't think it's illegal, but it's just like being an arms dealer. You'll make enemies if you sell arms to the wrong people. But I don't think it's really a matter of the law. It's a matter of what the market will bear. And so what they usually do is they sell to everybody and they try to conceal that. And they only stay in business as long as they can hide their dirty sales.
But NSO is also doing pretty good business, right?
They were very effective. They were Israeli ex-military. They were tied into the Israeli military, and the Israeli government approved them and supported them. But they sold to NATO members, and then they sold to NATO enemies. And when the NATO members found that out, they got mad at them and quit buying from them, and that crashed them. So, yeah, I think it's very much like physical arms, like people that make guns or bombs or missiles. That's not illegal, although there are some restrictions. But
and you don't see company doing that kind of stuff in the U.S.
There are exploit brokers in the U.S., but I don't know one selling malicious tools. Well, There's Metasploit, for example. Metasploit is an attack suite, and they do sell the one that everybody uses.
It's not zero day, right?
No, but they sell. There's a professional tool everybody uses for pen tests. Cobalt Strike, and there's 2 or 3 others, and some of those are American. So you can make those and sell them, and that's pretty much the same thing. Bad guys use it too.
But they advertise this as a help, IT
Yes.
guys.
Well, the technical term is dual-purpose tools. There's a lot of, like Metasploit. It can be used by bad guys and good guys. So it's like a gun. It's the tool itself doesn't mean you're a good guy. They make some effort not to deliberately sell to bad guys. So the Cobalt Strike the bad guys use is like a stolen hacked version. But it's very much the same. It does go on here. However, I'm not aware of people selling really powerful stuff here. That mostly seems to come from other countries.
But people still using Cobalt Strike, stuff to hack other people.
Absolutely. Criminals using Cobalt Strike all the time. This is why there's just a couple days ago, a bunch of signatures were released to detect in your IDS system all the old versions of Cobalt Strike. because they say the new version, legitimate people will have it. The old version and the hacked versions the criminals are using, before nobody would detect them with any of the tools, but now they're going to detect the old versions. They're trying to deal with this fact. A bunch of criminals are using it, and that's fouling up everybody. So it's a problem. Yeah, that's a very good question. Anyway, then there's DIL load order hijacking, which we did in the 126 class. When you launch your program, like you saw, Notepad has 20 or 30 DILs it needs to load. So it tries to find those DILs. The problem is it might load them from the wrong folder. Now, there is a known DILs registry key that lists known system DILs and shows where they should be. So if you look here, this is the known DILs registry key, and it has a directory, DIL directory, which is system root system32, and it has a list of DILs, and all those DILs, it will only load from that directory. So if everything was in here, you couldn't do DIL load order hijacking, but in practice, many applications load DILs that are not on this list, and if they aren't on this list, then it goes through a search. Starts from the directory where the application started, the current working directory, system32, system root, then it goes through the path variables, so it hooks other places. So you could put, for example, a floppy disk or a USB stick with an application. This is how the Stuxnet attack works. You had an application and you had a DIL right in the same folder, and it would load from that folder. So now you loaded that other DIL in here, and this is called, DIL load order hijacking. You put a DIL in the unexpected folder, and it loads it instead of the valid system DIL. So it works if the legitimate DIL is not in known DILs, and you don't have the legitimate DIL in the same directory, and you don't use an absolute path to load the DIL, then it will hunt for the DIL, and you have a chance to insert a Trojan copy of the DIL somewhere. So here's one. Windows Explorer was vulnerable, NTS HRUI. And you could put one in system root, and it would launch when Explorer does. All right. You could put it in the root of C, for example. So there's another, and Microsoft is still using the legacy printer spool protocol. Yes. Yeah, printer spool is the one that has quite a few vulnerabilities. Print Nightmare is one of the ones that's out there now. There's a lot of spooler vulnerabilities, absolutely. There's a lot of old code in Microsoft operating system in order to be compatible with old software. That's the root cause of many of the vulnerabilities in Windows, is it has a whole bunch of old code for old software in it. Whereas Apple just abandons anything 2 versions back and doesn't support it anymore, which makes it easier to secure it, but it makes it less useful for business, because businesses often have old code they want to keep using for years and years. And they don't want to be told they have to rewrite their old code just because the computer manufacturers decided to change things. By the way, I found out who was on the CPTC team, and they all got extra credit, but people who were doing NCL should let me know. Put a message in the Canvas or something, I know, to give you some points. Be good if you tell me like what your score was or something. That's worth extra credit too, but you need to tell me if you did NCL. All right. All right, so what technique creates job files? They call it recurring tasks. Microsoft's official term, I think, is task scheduler. That's what does that, makes job files. Startup folders just use shortcuts to the executable. They don't use any kind of special file, just a shortcut. All right, what technique is in the app data directory? Yeah, that's where the startup folders are, a long path in the app data directory. All right, you press shift 5 times, what happens? That's sticky keys, good for handicapped accessibility. All right, and what does WRP prevent? That's Windows Resource Protection, stops you from modifying system files. Good. All right. I think that's Ina. I don't know who that is. I'm not getting points though. I think that's not a real student. But this is a real student. All right. Stop the recording.